All right, well, we'll move on to our next talk by Anthony, who's representing quite a few different institutions right here. He's going to tell us a little bit about quantum Gibbs sampling. So we'll let you take it away.
Hey, thanks for a nice introduction. You hear me now? Okay. So I'm Anthony. I'm currently affiliated with Berkeley and MIT, I believe. But this work is largely done with my PhD at Caltech. And then, I don't know if you guys have heard this terminology, this Gibbs sampling. It's, I would say it is like a different way of calling thermalization. I heard a lot of thermalization being discussed in this workshop, but I'll try to define it precisely. And then sort of the reason why this quantum Gibbs sampling term was coined is really coming from classical computer science. Like people study, algorithms to prepare Gibbs states, the thermal states, and we put a quantum because now we're interested in quantum thermal states. Okay, and then as we warned you, some of these ideas were really been borrowed from quantum computing or even classical computer science. And then please stop me anytime because if this doesn't look very standard to you. Okay. All right, let's get started. So this is our the main thing we're interested in. We're interested in the Gibbs state, right? So quite often, at least what I was learning in undergrad is that a quantum system often likes to be in the Gibbs state. And then that's quite often the starting point of any calculation, or that's how you set up your problem. However, I've actually didn't quite learn how whether there's explanation of how this actually happened. It just ends up being somehow very, very useful and empirically very nice way to describe this quantum system in sort of an open system, like without isolation. Yeah, quite often we use Gibbs states or ground state, which is a very low temperature state, to describe these atomic physics, materials, and chemicals. And there's also how a lot of numerical methods are being done. It's just all you need to know is the Hamiltonian, and you can define this guy with the Gibbs state, and then you can squeeze out new physics out of it. Okay. So this would be a definition of thermalization: is that when your state is in a Gibbs state. That's what we call thermalization. Okay. In this talk, that's what it will mean. Okay. And so one of the perspectives that this talk is going to bring you is is this about quantum computers. Okay. So recently, from the other side of quantum science, there are a lot of computer scientists and experimentalists who are trying to build a quantum computer. And one thing they have been very interested in is, assuming you have a good quantum computer that's perfect, in this abstract theoretical model, can you simulate physics very effectively? So this is by no means a very new idea. It's actually go back to Feynman, and now this problem has really been sharpened in many ways, and we'll try to take steps along this direction. Okay. So for those of you who are maybe less familiar, this is the basic model, right? You assume that you have a perfect quantum computer that it's operating on a bunch of qubits, and then you can implement some set of gates. Usually they're pretty simple gates, just like classical logic gates. And then in the end, you also allowed to do measurements. Okay. Okay, so if you have this model and then someone gives you a good quantum algorithm, the quantum simulation algorithm, and lets you to access thermal physics or of interesting physical system, that seems to be a pretty useful device. Okay. So in a more recent way people think about quantum simulation is that people often talk about quantum advantage. So people hope that quantum computers can bring us sort of new aspects into science, in particular through this quantum simulation problem. Okay. So you might have heard when people talk about quantum advantage, people also talk about this factoring, which is like a mathematically very useful problem. It's very nice in solving cryptography. But today we'll just sort of think about this quantum simulation as a potentially new way to do physics. And if you're familiar with this quantum algorithm development, there has been a lot of effort in the past, I would say 20 years, 30 years, that people have been developing lots of algorithms to simulate Hamiltonian, in some sense, the Schrödinger equation, or the more complex versions of those. However, as of today, it still remains not very clear where do a computational quantum computation advantage, where that would occur, in what setting. Okay, so even still today, even this factoring has been very nicely sort of considered as a solid example with big quantum speedups. It's still not very clear where in quantum simulation could leave you like practical big advantage. And part of the reason is that there are just quite a lot few systems. The problem is not as well defined as integer factorization. There's bosonic system, there's fermionic. You can ask about many different type of problem. If you want to care about static, dynamics, or transport, you can really list a lot of physical properties you might care about. And who knows where quantum advantage lies in. And at the same time, a lot of the classical algorithm developers are still working very hard and producing better and better classical heuristics that quite often just works. In chemistry, people use DFT. Sometimes they use quantum Monte Carlo or tensor networks. That sometimes works. You kind of know that it probably wouldn't work all the time, but it's just very hard to know which problems are easy, which problems are actually hard. And at the same time, if you're a quantum algorithm developer, you feel kind of unfair because classical computer exists, they can use it. But quantum computer, don't quite exist yet. And it's hard for you to test and run your favorite heuristic algorithm. So one big problem now in the search of quantum advantage in simulating physical system is you often have to prove that your algorithm works. And that's arguably a pretty big bottleneck in finding advantage there. Okay, and sort of one of the theme of today is to argue that we try to locate more precisely where there will be interesting quantum advantage, and somehow thermodynamics, in the sense I will define more precisely, seems to have this character. And then sort of the suitable algorithm that's correspond to this task is this Quantum Gibbs sampling, as I advertise as a title. And so far the speed up we can get arguably is still it's still far from what practically what's practically usable. However, you can still kind of argue in some finely tuned cases there are speed ups assuming some complexity theoretic assumption. So I don't know if I have time to go through this, but I'll do that. At least I'll cover so what this algorithm is and then how it's actually quite connected to physics. Okay. All right. So if I just ask you, I want to prepare the thermal state of your favorite material or your favorite strongly interacting quantum system. And a very natural thought is, if nature is able to do it, why don't I just simulate that? So this is, it might look very naive, but actually this is quite a viable way if you put enough effort and try to make this precise. Okay. Right. So if you think about this, if you think about this in the lens of computation or sense of algorithm designer, you realize that your physics experimental friends has almost created a quantum computer. But however, it's kind of only capable. Currently, mostly it's only capable of doing one thing, is to cool things down. And indeed, at this regime, this is when very interesting low temperature physics arises. Now we have to be somewhat careful in constructing this refrigerator. But once you have one, you can really use it in many situations. And then, so the guiding principle is somewhat simple. If you would say, okay, it's thermodynamics, right? Thermodynamics got to work. However, this device actually have a lot of features that is kind of shocking as a quantum algorithm designer. Usually quantum algorithms are thought of as pretty, sensitive, easy to break. However, this cooling device that experimentalists have is actually pretty robust. You could start with pretty arbitrary initial conditions, and it would usually pretty quickly get to a low temperature state. It's pretty tolerant to some noise, if not too much noise. And then it just seems to work across many, many different kind of systems. So a starting point of this line of thought is, could we write down a very simple model of this guy? Right, so you can say, okay, let me just do a big problem simulation of the whole refrigerator as, just include the environment, and let me just simulate that. I just treat it as a closed system. However, usually the bath, this whole refrigerator is usually much bigger than the sample itself. So in some sense, the question more precisely is, could you have a quantum algorithm that succinctly capture the effect of this huge refrigerator and then implement that using much fewer, precisely controlled qubits? So we want a simple model for that. Okay. Okay, so if you want to do, if you want to describe open system, we have to start writing down Lambda-Adians. I think the audience should be somewhat familiar with this. But to quickly recap, the central object we'll think about is a continuous time Markov process. Some people call it Lambda-Adian, or you can think of it as a quantum Markov chain. It takes this general form to ensure that this is a physical map, and there's this kind of Hamiltonian-looking term, and then like a derivative term. And these L are also the Lindblad operator. I think some people call it jump operators. And then, if you evolve your system under this open system dynamics, this is the equation of motion you get. Okay, so this shouldn't be surprising. However, if you ask, what is the Lindbladian that describes my refrigerator? And suddenly this becomes a little more complicated, because the bath, the whole setup is a bit more complicated. And here we actually just consider even the most basic physical model. I think wouldn't satisfy most of the audience, but this is the model that we can make progress on. Okay, so we consider an open system setting with a very weak coupling to a very nice Markovian thermal bath. So this kind of thing was discussed, very, very early, a long time ago. And then recently, there's still some progress on simplifying this setup. Okay, so here's the setting. You have your favorite Hamiltonian here, and then you have your bath here. Bath is usually some pretty simple, some free Hamiltonian, and then you couple them with some pairs of simple interactions. And then it's kind of like a very nice story from this open system literature, that you can, under some approximations and conditions, you can get an effective Lindbladian that depends on all the parameters. Why is this helpful? Because what happens here is that the bath actually got, in some sense, is integrated out. You can more or less throw away the bath, and instead only keep some microscopic parameters, like temperature or some other, something like correlation function. Yeah, so if this goes through, then this seems to be a candidate of what we might want to simulate. Okay. However, there's actually some challenge here, and the reason why there's still so very recent follow-ups is that there's lots of approximation that comes in here, and then some of them are kind of okay, some of them are actually very dangerous. Some of them actually only works for finite size system. That doesn't work for many body system. Okay. So here's sort of like a catalog of existing approaches. I'm just going to list them here. So there's something called Davis generator that maybe not only known for some specialists. But there, what they do is to say that, okay, my system is going to be finite size, and everything else is going to be infinitely large or infinitely slow or infinitely weak. And then you can arrive at a pretty nice analytic and explicit form of this open system dynamics. However, however, this really only works for, I think, optical system where you have a few levels. Like if you have many body system, that's what these other work trying to address. Doesn't end up being getting like a sort of mathematically succinct description of the Lindblad. And they really take a lot of very, very different forms. It's what I could just say is that if you try to compare it with what's the classical analog of this, right? What would that be? That's the classical, the Glauber dynamics. Somehow Glauber dynamics is just so much simpler. So it's so much better sort of mathematical property. So the Gibbs state was going to be the stationary state of the fixed point of this distributive process, a very simple mathematical form that people can start proving things about it. And also, it's like a very local dynamics that in some sense make it very physical and very efficient. And so in contrast, all of these other ones, they sort of importantly lose locality. So in the end, you get like a very non-local Lagrangian that each time you hit it with a jump, you have to kind of see the whole system. Right. So you can just make So you can make these A and B like local polys. So you can, this is very physical. You can even can attach only to the boundary. However, what happens is this Hamiltonian will actually scramble them. And then if you didn't do it correctly, like it somehow just spread out the whole system. Exactly. Yeah. Yeah. This will be the main point. Yes. Yeah. This model looks completely simple, right? The Hamiltonian, and then there's like some local jump, and then a pretty simple path. But this ends up being just very complicated. Yeah. Right. So here, so the hope is that could there be like quantum version of Glauber dynamics, where maybe you can do some approximation, but you kind of want to recover all nice properties of this classical Glauber dynamics. That is algorithmically efficient, has nice properties, and still somewhat physical. And somehow, the resolution of this question, we have to borrow some insights from computer science. So that kind of bridges to the second motive, which goes to actually how classical people have simulated classical thermodynamics. Right. So if you ask again, if I want to simulate a thermal state, what can I do? Actually, if you ask a classical numerical person, they would say, "Oh, I can run Monte Carlo." That allows me to simulate my favorite icing model. And yeah, so that's will actually be where we will pick up and then try to develop along that direction. Okay. So here is a abstract description of the metropolis sampling algorithm that I think some of you must have implemented. It's a really old algorithm, but still being used today. Okay. So as a user, all you need to do is to input these parameters. Right? You need to specify your Hamiltonian. Right? For example, it could be an icing model. Right? You can just put it on spins. And you will pick a temperature that you would like. And also some set of so-called jumps that will flip some spins. Right? In this case, it's very natural to think about the case we just flip one spin at a time. Right? If these are like a 2D grid, and you just pick randomly one side and then flip it. Okay, makes sense. Now, of course, you could choose different ones. If you can also say, okay, I want to flip everything all at once. These are so-called cluster updates that sometimes will accelerate the mixing of these models. But right now, these single spin flips are just pretty natural. Yeah. Right. So let me just show you this animation. So I think this model is an icing model with some temperature, some constant, and then I think there's a magnetic field. And you start with the spin pointing at the opposite of the field. And then what will happen is that these guys just align with the magnetic field. Okay, and you see that this algorithm just converges very quickly. As it looks, quickly grows, and then you kind of saturate it. And then I believe that in this case, people can even just prove that this algorithm just converges to the stationary state, which is the Gibbs state. And then, the way people use this algorithm is that they will just start tuning these parameters, and then at some point you will start seeing phase transition that these things actually got very slow, or you start seeing to a different kind of order. Then maybe these spins start getting stuck. So by running this numerical experiment, you can just explore the phase diagram of your favorite model. So if you have a version of this in the quantum world, that seems pretty useful. Right, so just to recap, Markov chain Monte Carlo, and I also just recently started to learn, it is still a very, very active story. Even though it's introduced like 70 years ago, people are still working on it, trying to prove mixing times. So initially, these methods are, I guess, are invented to simulate physics. And Ising model was kind of one of the earlier attempts. Nowadays, there's sort of lots of variants, and even you can do this some more quantum versions like Quantum Monte Carlo. But also, these algorithms are just so nice and so robust that people just use them to sample sort of other sort of combinatorial objects that may not have origin in physics, but it works. So sometimes you can even prove that it works. It's also being often used as a heuristic for other optimization problems. That's just being used quite a lot these days. So you really hope that if classical MCMC is really that great, maybe we would like to have a quantum version of it. Okay. Right. So classical power dynamic is one of the Markov chain Monte Carlo methods. Yeah. But so right. So for example, if you want to simulate phase diagram Ising model, you can run the discrete time chain or the continuous time chain. There's really not that big of a difference, but there's just different ones you can run. I think in computers, discrete time is easier to run. However, for physics, if you like a continuous time Markovian dynamics, usually you would do the Gilbert, which is a continuous time one. Okay, so I think the power is that you can do both. So you can really run this algorithm and just directly see what happens. And then there's like a long-going effort from the theoretical part to really prove that it works. You can start with any choice of initial condition, and it will mix to the thermal state. It is still an ongoing effort. I think people have been pretty successful with Ising models, but once you change the model, it's still ongoing effort. So the tricky part is that sometimes your system becomes a memory, like Ising model. Then it wouldn't, and then it would stop mixing. And then if you want to characterize exactly when that happens, it requires some luck and very good, some hard analysis tools to tackle these problems. Right, so just want to quickly mention the principle of Markov chain Monte Carlo, because we'll just try to generalize this to the quantum case. So very abstractly, here are the principles, right? So you want a Markov chain M, which is like a probabilistic, kind of like a random walk, where this random walk has this property that it fixes the thermal state. So if you start thermal, it would remain thermal. And then you also hope that wherever you start, this chain would quickly converge to your ideal thermal distribution. And then if this is the case, then algorithm calls is pretty simple. Just how many times you're going to run it, time the calls per step. Okay. But of course, so the whole difficulty is to prove that this guy converges efficiently in finite times. Then you shouldn't. Okay. And the goal is to know exactly where that happens, and that indicates a phase transition. So in some sense, like there are different things that you might want out of this this MCMC. Right? You might if it's serious, you can say I want to prove that it converges when it should. However, if you're interested in physics, if you're interested in phase transition, you actually want to know the opposite. You want to know when this failed, because there's also if you take this as a model of physics, just tell you when phase transition happens. So it's really like both sides. Either it's not mixing or mixing. It's all pretty cool. And as the audience has already mentioned, this one of the key recipe in designing to making both of these criteria hold is called detail balanced. It's like an additional condition that you put on this Markov chain M. Is this some kind of symmetry? It says that as stationarity, the mass sort of flowing across different dimensions, you cancel each other. And since the stationary state is the Gibbs state, right, it boils down to this relation between sort of the heating and the cooling process. And this is kind of built in the Metropolis rule. If you have seen how they implement this algorithm, you really want these two to relate it by a Boltzmann factor. And then here, so the important thing is that it really don't only care about the relative, so how energies are different. It doesn't care about the global energy. However, once you can imagine if you change this up, right? If all the relative, the ratio is all correct, it really does give you the Gibbs state in the end. Right, so this simple looking condition is nice because it's a very simple recipe to give you thermal states. But that's not the only reason why people like it. People like it because there are several simultaneously nice properties. So not only is it formally convenient, it's actually also algorithmically efficient, because in this description you only care about energy difference. So what it means is that if you want to implement this detail balance, all you need to do, when you flip a spin, is to look at its neighbors, because all you care about is energy difference. You don't really care about the global energy, but really only the local energy. And this is what makes this algorithm so efficient. And for the theorist, this detail balance condition make things very mathematically very natural, because it introduce and make the idea of spectral gap very useful, and also basically make the Markov chain Hermitian. Okay. So now you will say that, okay, maybe I would also like a version of this in a quantum world. But then things start becoming less trivial. So in a quantum world, so the detail balance can be represented in this 2D figure. So the reason why it's 2D is because you have Bros and Ketz, right? Your input state rho can be decomposed into sum over Bros and Ketz. And then if you write it down in the energy basis, these are psi1 are all eigenstates. And then what you kind of want is that between all the pairs of Bros and Ketz, when you evaluate this Lambdatian, so the rates of these two have to obey this Boltzmann rule. However, you see that there's some conceptual differences, right? Classically, you really know what these configurations are. They're just some configuration of spins, and you also know the energy. So like this, computing this number is pretty simple, and you can also do it on the go. Right? You can just check, okay, if I flip a spin, what does energy change? I can compute that and then just know what this number should be. However, what's sort of interesting here, what's the challenge here, is that nobody really tells you what the energy eigenstate should be. If it's a strongly interacting many-body system, well, it's already very challenging to even write them down. Right? And even if you have a quantum computer and you want to measure the energy, that's also very expensive. So there are sort of two simultaneous problems, if you want to enforce this condition. This. All right. So if you right, if you evaluate the matrix element between this as the input and this as the right, so I can write it down, I guess. Right, so it's something like this. Because now these guys are super operators, and the input is density, output is also a matrix, so you kind of have to worry about these 4-point kind of object. Yeah. Right. So what actually people try is to start with a discrete time and end up bumping into lots of problems. And what ends up being the most natural one is to think about it in continuous time. Somehow it's easier. A priori, I might want a discrete time because that seems easier to implement. But there seems to be some technicality that makes continuous time easier to make detailed balance. And I will actually just discuss this. Right. So let's say we want to implement this. Right. We want to achieve detailed balance. Right. Here's what you might want to do. So let's lay out our eigenstates in an energy basis in the order. These are, say, JRs, they are the energy states. And let's say we want to make this metropolis rule. Right? We apply a jump A, this could be a single Pauli. And then we want to say, if the energy decreases, we want to accept, if it increases, we want to reject this, the correct probability. This is the metropolis rule. Right, so you can imagine, once you apply a jump, the chance of it ends up being at psi j is given by this amplitude squared. Makes sense? And then you want to say that, once in a while, with this probability, I want to reject. Right, this is easy if you know what the state you want to reject to be. Right, if you know what these states are, this is easy to do it. Right, you can just trust this and then sort of prepare this again. But you kind of don't want to do that because quantum states are pretty, you're not going to clone them, right? So the two key conceptual challenge here is first, no cloning, right? How do you reject without having lots of copies of the same states? And second, you somehow also need to know what the energy is, right? So you have to do some kind of measurements, but you have to be very careful, because after you do the measurements, you have to try to go back once in a while. Right? So these two actually kind of compound each other, and both of them are quantum mechanical. Yes, this is fully fully quantum. Classically, if you have the full matrix, well, you already solved the problem, right? If you can just do a single eigenvalue decomposition, you really solve the whole matrix. But matrix is very big. Right here, you're really operating on sort of quantum state that's very delicate and you don't have copies of.
Classical physics, I have a huge system. I don't keep track of all the possible states, but I can sample it. I can start somewhere, apply this procedure.
Right, exactly. Right, exactly. So oh, okay. So right. Suppose at at this instance well, okay, but then requires you to basically write down the quantum states. Right? Sure. Yeah. In that, I think that people actually do that, but once you do that, it's exponential cost. So I agree that if you already know what these guys are, you can lay them out, and you can really just do a classical random walk on the eigenstates. And that works. However, the challenge is how do you do that without writing them down? And then how do you do the quantum leap? And in fact, this is one of the earliest attempts and lead to a very complicated algorithm. So in some sense, these can be avoided somewhat, but we'll give you a much, we'll soon give you a much simpler and more direct result. So what's been known, some people approach this problem by assuming energy measurements are perfect. This kind of works when commuting Hamiltonians. We really, the energies can have well-defined gaps. Of course, for these models, it doesn't really work with a many-body system where the level spacing is very small, exponentially small. So there's these other proposals that try to deal with imprecise energy measurements, but then this seems to bring lots of trouble. Some of them are not proven, and we don't even know what the fixed point are. And sometimes detail balance is broken, and then this really causes a pain in analysis. Okay? So if you compare it with classical MCMC principles, have exact detail balance, have a very simple form, and also a very local and cheap algorithm.
Very local, simple to understand. Really cost of storing of quantum state. Once I have a quantum state, I'll act on it local operator and accept or reject on my classical computer. That does work.
That works. Okay. Yeah, but if you already right, these are all quantum algorithms. Yeah. Okay. So so we have now just discussed two very different ways of looking at basically the same problem. We want to prepare a thermal state, this Gibbs distribution, and then from the physical side, you can ask what is the right model of a refrigerator, right? On the computer science side, if you would just work backwards, if you just say I want detail balance, what is the algorithm that achieves that? These two two conceptually different way, but we'll see that they basically can be resolved in this one sort of equation. Okay. Right, so here comes the main results. That was I think a year old in these two papers with Michael Fernando and Andras. So in this work, we claim to have found a quantum version of global dynamics. Okay. So here's a guarantee. So if someone, for any Hamiltonian you would like to understand its thermal properties, say it's like a 2D lattice, and you pick your favorite temperature, inverse temperature beta, and pick your favorite set of jumps. This could be single polys, for example. There is an algorithmic construction of a Lindbladian. We can write it down with the following simultaneous properties that arguably matches global dynamics. Okay, so the first one is detail balance. So this Lindbladian we have satisfies exactly the quantum detail balance condition. Therefore, the thermal state is, by construction, stationary. If you start thermal, you remain thermal. Okay? And second, there is an efficient algorithm to simulate the dynamics at some very efficient cost. Okay, so this problem doesn't mean anything to you, but this is also basically the optimal, more or less optimal thing you can do. And I would like to emphasize is that this algorithm is also local. In a sense, very similar to what these classical Markov chain Monte Carlo algorithm are. So if the Hamiltonian and jumps are local, so for example, like a 2D lattice with single side flips, like Ising model, then this Lindbladian we construct is also quasi-local. So it's not exactly local because of quantum effects. And then so the uncertainty, or like the radius of the spread of this Lindbladian jumps is roughly order beta. So this is the only time scale in the system.
So previously show us the equation of the Lindbladian. This one we constructed different.
This is a particular form. Right? So there's the abstract Lindbladian equation that always have to look like that. And we in particular give an instance of that. Yeah. So in particular, for commuting Hamiltonians or classical Hamiltonians, this light cone actually become constant size. And this reduces to what people have known already. So in particular, it recovers global dynamics if you start with the diagonal inputs. Okay, any questions? Right, this is something you can choose. You could choose them to be local flips. Maybe that models your, maybe not that's what your physical model is. But you can also choose fancier ones. You can once in a while flip every site. And that in the case of classical icing model, that's what leads to a fast mixing. So there is some flexibility.
The Gibbs state in the end, there's some criteria for taking
So that often requires some good intuition. So again, like this 2D icing model example, if you have only local jumps and the temperature is very low, then it doesn't mix. It's kind of memory. It has protect all up or all downs. However, if you decided to flip all the spins, then it actually mixes very quickly. And then proving the mixing time is like a long program that computer scientists have been doing for a long time. And in some sense, so this map defines a lot of Markov chain mixing time problem for a wild family of different models. You can pick your favorite one and then ask, oh, is it that rapid mixing or not? If it's not, it probably means that there's some interesting phase transition happening. Okay. All right, so let me just emphasize sort of the conceptual, how do we can reconcile this problem? So recall this quantum detail balance is some pairwise exact relation between pairs of eigenstates, where you don't really know what eigenstates are, and you also don't like to measure them too precisely. Right, these are the two challenges. So the reason why we end up able to kind of overcome these two issues is to realize that we don't actually need to know the energy very precisely to enforce detailed balance. So this is kind of a pretty cute thing. So for example, if you have worked on quantum algorithm, this is the operator that one can implement efficiently. This is the Hamiltonian simulation problem. And here, you'll see that this is a function that depends exactly on the energy eigenstates. And then you have, and if you write it in an energy base, it looks like this exact form. However, quantum algorithm is able to do this smoothly without sort of perturbing the system that much. It doesn't necessarily need to decohere all of them in order to implement a smooth function. And that's end up being what's happening in our case. So somehow detailed balance is also more like a smooth weighting on the transitions. And the second cool thing is that the energy difference is actually a quasi-local quantity. Right? If you think about, if I want to, if I flip a spin, you can ask how much energy has changed. To know that, you just need to look local. Right? That's in the classical case, you just need to just poke each of the sites, and that's enough. In a quantum case, somehow because quantum they actually spread out a bit more, you actually have to look in the neighborhood. But the neighborhood has radius just beta. It's a constant if you have constant temperature. So this kind of get away, without actually seeing the full system, and only looking at things locally. So you end up, getting some kind of really global dynamics that you can just flip each site, and then the moves are all localized. Okay. No questions? Okay. Right. So with this, let me just kind of emphasize, so kind of give like a broader picture. So in the beginning, I've told you that we want to understand how the Gibbs state kind of arises, right? And then this Gibbs state people have been studying without thinking about where it came from. People can study all sort of physical properties, right? Think about decay of correlation as a measure of phase transitions. You can think about Markov property. That's what classical people really, really like. And now, what I'm suggesting is here's a dynamical way to think about Gibbs states. In a way that is very natural, so closely related to an open system thermalization. It arises in this weak coupling limit. Maybe you don't like it, but at least to give you a map that behaves like a global dynamics in the classical world. And then you can try to kind of make this connection between static and dynamics. Whenever you see your Gibbs state have a decay of correlation, you'll be tempting to ask, does it also mix very quickly? This is not obvious, but in a classical case, this seems to be an equivalence, an exact equivalence. People actually have write-down condition of about decay of correlation that allows you to prove rapid mixing, and then vice versa. But in the classical world, this is actually a pretty nice and a non-trivial relation between statics and dynamics. We don't know if it is true in a quantum case, and so far we have only established like a mixing time at very high temperatures. And all these things you can try to relate to dynamics versions of this. Markov property for some of them. For some of you who might interested in this information theoretic things, you can think about invariance and recovery maps. With the static phase transition, you can think about dynamical phase transition. Whether they always coincide with each other, we don't actually know. And for some of you who might like this quantum memories, when you see an invariant that's slow mixing, that's actually makes it a candidate for a memory. This is actually a necessary condition for a memory. And so previously, this maps is not really well defined for non-commuting systems. So previously, the study of self-correcting memory is restricted to commuting models. And here we give you a map that allows you to make this very precise. So in the remaining time, let me just tell you what this map is, what the construction is. So a key property, a key operator that is in our construction is this operator. So for your target Hamiltonian H, and then your favorite jump, like a Pauli, consider a Fourier transform of the Heisenberg dynamics. All right, so this object depends on a real number omega, and also some kind of filter. And then here, let's just take the filter to be a Gaussian. All right, so what's happening here? So you evolve your operator for different times, and you do like a coherent linear kind of Fourier transform all of these guys. Right, what does it do? Oh no, this roughly captures it selects the transitions with energy difference roughly omega. Right, if you go through a Fourier transform, this is really what it selects. So pictorially, kind of choose all the jumps that change energy by roughly omega, and there is still some uncertainty. And you can see that this guy really depends on energy difference, right? Because you're sandwiching with H and H and minus H. And it only depends on the Heisenberg dynamics. And if you only evolve this for a short time, it is localized because of Lie Robinson bounds. Okay, and then with this this object, right? It may not still be obvious why you can get detailed bands, right? Because still there's some uncertainty. But somehow what's happening is that Gaussian has this remarkable, just some nice arithmetic property that is so similar with convolutions. And then you have this exact relation with itself. So what's happening here is that even though the uncertainties are Gaussians, you actually know what they behave when you kind of have another layer of uncertainty with it. So this probably doesn't make full sense, but what I'm just saying is that because you actually exactly know what these filters look like, you really know what the uncertainty looks like. When you manipulate them, they actually remains Gaussian. So if you pick very, very careful choice of this function, it actually can allow you to recover exact detail bands if you choose things very, very precisely. Okay. So this argument really breaks if you choose a different filter. So really everything is kind of built around Gaussians. Okay, so this is the full embodiment. It looks like this. So you take this thing I told you, this is some kind of energy measurements about the energy difference, omega. And you build a embodiment out of this, and then you put a weight depending on omegas. And these weights look pretty familiar to the classical case, right? You kind of want this Boltzmann, this Boltzmann-looking relation. You really just put them here, and you weight this transition by this rule. And so there's one extra term that I haven't really told you where it came from, but with this guy actually also plays a role in making detail bands exact. So this is like an inherently quantum effects where it actually is a unique solution to detail bands. Like this guy also have to take a very exact form to make sure the whole thing is detail balanced. Okay, but now this is a fully well-defined version of quantum global dynamics. You can write it down, and people actually have proved things using this. Okay. Okay. For those of you who are interested in algorithms, there's also a primitive that implements this A of omega operator. It really is a version of phase estimation for operators. Has a somewhat direct correspondence to the phase estimation. I'm just showing you this in case you're interested in the algorithm part. Okay, but this is all nicely handled in our paper. And I guess I don't have time, but let me just conclude by just saying that out of these analyses, there's a sequence of follow-up works that try to build on this Gibbs sampling route from very, very different angles and try to argue, and try to found quantum advantage. And we kind of give a series of different arguments, and some of the authors are actually in the audience. You can chat with them as well. Really have learned a lot from very different aspects. Let me just show this summary table. So you might say, with this Gibbs sampling, it seems very cool, but does it really do anything new? And here are the summary of what we know. So if you allow me to tune down temperature to be very low, inverse polynomially small temperatures, then there is a family of 2D non-commuting Hamiltonians where it's for Cooley is rapidly convergent, and the ground state is classically hard as it encodes any computation you would like. So in other words, if you have a big refrigerator that's very, very low temperature, that's also a quantum computer, roughly. And then if you don't like low temperatures, we also have results on constant temperature. All the authors actually in the audience, where even constant temperature with commuting Hamiltonian with constant body interactions is as hard as some of these random circuit sampling tasks. Okay. And more recently, even if you relax it, you don't even consider thermal state, but just any state with a constant energy density. And with the random few body interactions, such as SYK model, quantum algorithm can found those energy states, but nevertheless, all those states are very complex in a sense that it necessarily requires a very deep circuit to generate them. Okay. So I think I would just stop here because I'm using too much time. And this is the outlook. Oh, okay.
Great. Thank you very much. All right, we have a few minutes for questions for our speaker.
Can you comment on relations between evolution under this kind of Lambdadian and evolution under the Hamiltonian that's thermalizing?
Right. So it's actually not entirely clear. So classically, evolution by the Hamiltonian itself, you take Ising model and you do that, nothing really happens. And then classically, if you study thermalization of classical Ising model, you really need this external thing to drive the transitions. And quantumly, it's somehow because the Hamiltonian is non-commuting, many Hamiltonians seems to be thermalizing just by its own. And that is fact seems a bit harder to capture. Like here, the approach here, the approach we take here is really open system approach. We don't know, I actually don't know how these would interplay with each other. So I think in practice, I think both would play a role in thermalization.
But in Hamiltonians in which subsystems are expected to thermalize, are late time behaviors of local observables expected to be about the same for Hamiltonian dynamics and dynamics under this Lambdadian?
It's a bit unclear. I mean, it's a bit unclear in terms of what can be proven. But I believe that if you believe that Gibbs describe things and then Gibbs have decay of correlation, it doesn't depend so much on the boundary, then I think that is true. However, if your system has strong correlation, then it doesn't make sense to cut down a small piece. Right? The boundary could have a very strong effect. Then it becomes hard to think about small subsystems and big systems. So it really depends on the system. But if the system is kind of weakly interacting, then I think they will all give the same. Thermalization should always work.
Yeah. Okay.
I mean, one naive idea to prepare a refrigerator is to imagine like two systems of equal size, your system you want to cool and your refrigerant, and make the refrigerant have a Hamiltonian that that you can solve exactly. So you can prepare it in its ground state, then you weakly couple it, let the refrigerant heat up, throw it away, stick another ground state in. Does that work?
That works.
That works.
However, it's unclear whether that will be faster than this. So in order to be, so one thing that I think would happen is the coupling has to be weaker and weaker
as you go to lower temperature.
Lower temperature.
Also
have to be careful about the bath property. So the bath has to be very continuous in order to absorb arbitrarily small energy excitations.
You mean like the gaps have to be small?
So if the bath is like Ising model, it only eats up like a constant energy, and that's kind of not good if you want to go very low temperature.
I see.
So there's actually, I think that's actually a very what could be possible. Like maybe in future people actually do like something like that. But I think currently it's unclear what kind of bath would you want and how big it would be.
Mm-hmm.
And I think there's actually I think Google has some experiment doing this where the bath is like 1 qubit.
That's not so useful. Yeah, I see. But
I asked them, so what bath would you like? They certainly want bigger and so more continuous bath, but it may be too expensive. And you rather just have an algorithm that exactly know what you want.
Yeah, I see. Right. Thanks.
All right. So if you're very, very low temperatures, you have to be very careful about heating effects caused by the weak coupling. And then my numerical friends told me that it seems easy to make it thermalize if you're like a system bath at high temperatures, but the lower you go is actually harder and harder because the perturbation actually becomes energy scale gets to get relatively big at low temperatures.
Any more questions for our speaker?
In terms of the evolution under the coherent part of the Lindbladian, how does that differ from just like you mentioned that there's some non-trivial stuff you need to do with it. How does that differ from just evolution under the the Hamiltonian?
Right, they're very different. Yeah. So these terms look like lamp shift term if you ever know about open system. Like so these like yeah, this guy actually also has a kind of origin in open system. Like this term do have to take a particular form that depends also on these A omegas. But then the full Hamiltonian, if you want to model this as like an actual cooling experiment, there's a very big Hamiltonian term, and this is all kind of weak coupling, kind of it's weak perturbation to the Hamiltonian. But now you're on quantum computer, you can do whatever you want. So you can just drop the Hamiltonian term, maybe add it if you like. Yeah. But they will behave very different.
So this Lindbladian seems very finely engineered and
Yes.
fine-tuned. So how robust is this? Like if in actual implementation, you don't quite exactly implement that.
Right. So that right. I think the answer is it will probably not. It will be bad if you have lots of errors. I think it will just heat up the system very badly. So suddenly you need very good error correction. Like your quantum computers has to be very good. Otherwise, and so the noise from from the error would just heat up the system very badly.
But from the theory side, you have some
Robust analysis of you can tolerate some small perturbations. Say the filter is not exactly Gaussian and
But I don't think there will be very good theoretical bound because I think the stationary state would just be very, very high temperature. Even for a single qubit example, thermal noise, like high temperature noise, even a little bit would drastically heat up the system.
on a quantum computer, you could spin it.
Yes. Mm-hmm. Right. So usually that requires post-selection. So you can do it a few steps, but then, right. So let's try to imagine you run Markov Chen Monte Carlo, but each time you reject, you throw away the sample. And after n steps, the success probability actually just decreases with exponentially. But this one, so it recycles in some sense, and that's all the key part. Yeah. So a lot of the previous approach about Gibbs state, what they do is to start with a mixed state and then apply a big filter that has Boltzmann weight, but then the successful probability is exponentially, like it's just usually exponentially small. And it's so intrinsic. Like intrinsically, you really need to recycle the part that you didn't succeed. You kind of had to constantly. You don't like post-selection. I think there's not in this case. Don't do that. Yeah.
What did you say was the key technical? Was it Gaussian filter for
the key technical?
Innovation relative to the other approach? What problem?
Right. It really is how one can achieve detailed balance locally and efficiently and exactly. Because that's so the most. That's why classical MCMC is so successful.
I'm sure.
Yeah.
How does your approach help you do that? I'm sure other people are trying to do that.
I think previously we didn't know this is possible. Like because I also didn't realize it's possible. This is kind of accident. Because the fundamental conceptual barrier is like you don't know the energy, you also don't know what your state is. And how do you enforce this exact rule? And classically, this is all very simple. And this is the kind of thing that once you write it down and you check that, oh, it is detailed balance. This would be an example, but then before that, I didn't believe this until I read like this is fully worked out. Right. So each of these moves, it's actually a local map. So the cost is basically constant. Each move. And then if your system is rapid mixing, you kind of have to touch every side once. And that would be just relatively scaling with the system size.
Any more questions for us?